studying right now. We started with plate tectonics. Hopefully this looks familiar. This is where he said you left off last time. I'm also a wanderer, so just watch your feet. I'll try not to trip over anybody. So he said you guys left off about here last time, talking about different types of plate tectonics. And so what we're going on is we've got a space problem, because all these plates have to fit together like jigsaw pieces, but the Earth is a sphere. So if one plate moves, what's that going to do to all the other plates?
Shift.
It's going to shift them and jostle them and rub them and bump into them. So every time any plate moves, it's interacting with a surrounding plate. It's doing something to a neighbor plate. So what that means is that we have all these different types of interactions happening along the boundary. And when we have the plates pulling away from each other, you remember what that's called from last time? Yeah, there it is right there. So sneaky. It's divergence. I always tell my class to do hand motions. So I'll see students like sitting there on the test, like trying to remember with their hand motions what the different plate types are. Divergence is pulling away from each other. So if it helps you to make like a physical motion, I taught middle school for a couple years. Helps you to make a physical motion to remember things. Feel free to remember divergence. All right, what do we call it when the plates rub together? They mush into each other. Yeah, that's convergence. So they're pressing into each other. That's convergence. And then the type we didn't talk about last week is what happens up here and what happens down here, where you have plates going in different directions. So these little funny half arrows, they're a symbol that geologists like to use all the time, and they're showing that there's motion in opposite directions. So this plate is moving to our, if we face the screen, our left. The bottom plate is moving to our right. They're going in opposite directions, so the plates are sliding past each other. Do we remember what kind of boundary we call that one? What did you call it? Yeah, transform boundary. So that's called a transform boundary. So transform boundaries or transform faults. Another name for them are strike-slip faults. And strike-slip, just remember that means that they're moving kind of parallel to each other. They're not pulling apart from each other. They're not mushing into each other. They're sliding past each other. So one place where you get a lot of transform faults is along the mid-ocean ridge system. Now this is not a transform boundary. What kind of motion's going on here?
Divergence?
Yeah, you got a plate pulling away, and that's a divergent boundary. You got another divergent boundary up here. Plate pulling away. But look at this area right in the middle. What happens? The upper plate is going left, right there. The lower plate is going right there. And so they're going in opposite directions past each other. So that is a little bit of a transform boundary. So when we look at the pattern of the mid-ocean ridges on the map up here, you see there's a lot of these like big cracks where they're offset from each other. Those are all transform boundaries. Those are all places where the mid-ocean ridge system is offset places because of this opposite style of motion. I was going to say, there's a classic transform boundary here in Southern California. I don't know if you guys have ever heard of it. Big fault system, Southern California, makes giant earthquakes. Yeah, San Andreas. It's one of the classic transform boundaries. So there, the Pacific plate and our plate that we're on, the North American plate, are sliding past each other in that side-by-side motion. So that's a modern example of a transform boundary. All right, the other thing to talk about is hotspots. Hotspots are interesting because they don't actually follow the rules of plate tectonics. And each of those little red dots up there is a currently active hotspot. There's about 120 of them that have been mapped out. What do you notice about the relationship between the location of the hotspots and the boundaries between the tectonic plates?
They're not on boundaries.
Yeah, with rare exception being Iceland and the Galapagos isn't even that. Easter Island there. Canary hotspot. There's a couple exceptions. With rare exception, most of the hotspots aren't on the plate boundaries. So a hotspot is a volcano. It's a volcano that's not on a plate boundary. And there's a reason for that. Because hotspots have magma that magma and it's erupting out the top of my head, and a plate is sliding past me. I'm staying still, and a series of volcanoes are forming above my head, being carried away by the plate. And another one is forming above my head, being carried away by the plate. And a third one is forming above my head and being carried away by the plate. So that's what this picture is showing us here. The hot spot is making active volcanoes. And here the volcano is above the hot spot where the magma is coming out, so it's active. Here it's moved off the hot spot and it has died, or the volcano has died, and it's not making active magma anymore. And so it sinks down back under the ocean. And what you end up with is a chain of hot spots that tell you the motion of the plate. So it's really useful for tracking the modern motion and the past motion of tectonic plates, because it's giving you a literal track across the ocean or across the continent of where that plate has been. So if you look at Hawaii, here is the magma rising up to form the active hotspot, which is under the Big Island. In fact, the active hotspot has moved off of the Big Island and is starting to form a new, very small underwater volcano called the Weehee. And Weehee is not big enough to break the surface yet, but it is currently active underwater, and it will be the next Hawaiian island. So the Hawaiian Islands get older as you go to the northwest. So with the modern hotspot on the Big Island of Hawaii and Maui and Oahu, and then Kauai is the oldest one that's still above sea level, and this chain of hotspots even continues further on. So, bigger question, but not really, but you know. True or false? Hotspots always occur on plate edges. Who says true? Who says false? Alright, the falses have it, that is a false statement. Alright, so a couple of interesting things about plate tectonics. With the motion of the hotspots, with old geological deposits, with old rocks, with old plate boundaries, and fossils and things like that, we can kind of figure out where the plates have been in the past. So the plate reconstruction, or figuring out where plates have been over the past 540 million years, is pretty good. So you can see about 540 million years ago, most of the plates were down in the southern hemisphere, which is really interesting because we're used to seeing our globe as it is now, where most of our landmass is in the northern hemisphere. You know, our North America, Europe, Asia, most of our large landmasses are all in the northern hemisphere. Well, 540 million years ago, that was not the case. We had a lot more landmass at the South Pole in the southern hemisphere than in the northern hemisphere. And these guys go sliding around, and 480 million years ago, you see them here, 420, you see them here. What's happening here? Are they moving together, or are they kind of coming apart from each other?
Moving together.
Look at them, they're all mushing together. And then by about 180 million years ago, they're all joined up into that great big supercontinent called Pangea. Yeah, there it is right there. And then Pangea starts to break apart. The plates are drifting away from each other. Here they are 60 million years ago. Looks pretty much like now. Not a lot's changed in the last 60 million years. And here we are today. So a little bit of slithering around since then, but so you can, it's kind of fun to think about. Well, that raises the question of, are we still moving? I think we're still moving?
Yeah.
We are still moving. The North American plate is moving about a centimeter a year to the northwest. So we're slowly creeping up towards Canada. We're going to get colder, very slowly. Well, question, yeah?
Yeah, I'm sorry. How old are the Great Lakes? Because it looks like from this it's like 540 million years old.
Yeah, no, the Great Lakes are a very recent feature. I have a feeling Dr. Gillespie's going to talk about that when he talks about glaciers, because they're related to the last period of glaciation, which is only about 10 to 12,000 years ago. So before that, there were some river valleys in this part of Michigan, but there were no Great Lakes until about 10 to 15,000 years ago, not these millions of years ago. They're using kind of the generic outlines of the continents, and yeah, it's not quite 100% accurate what they have up there. Sea level rose and fell in Michigan a number of times. So if we keep sliding, this is what the world might look like in a couple million years from now. Kind of interesting. Not too much different. Everyone's split around a little bit. What's happening to the Atlantic Ocean here? The Atlantic is going to continue to get wider, so your New York to Paris flight might get a little bit longer. The Pacific is going to continue to shrink and get a little bit smaller, so your LA to Tokyo flight might get a little shorter. We still have, planes in a couple million years from now. But And if you, well not you, a substance fails on any one of these criteria, we can't consider it a mineral. It has to meet all 5 of these things. So some of these are pretty easy to explain. Some of these numbers 4 and 5 are going to take a little bit more effort to explain, but we'll get there. Naturally occurring is pretty obvious. Do people make minerals?
No.
No, people don't make minerals. Minerals, nature. Mother Nature makes minerals, not people. So if the diamond that you bought was grown in a lab somewhere, it is technically not considered a mineral because it was not naturally made, it was man-made. So it might be chemically indistinct and perfectly like a natural diamond, but we actually can't call it a mineral because it did not form in nature. It was grown in a lab. So anything grown in a lab or made by people would not be a mineral. Solid. That one seems pretty obvious too. Minerals can't be gases. Oxygen is not a mineral, it's a gas. Water, liquid water is not a mineral, it's a liquid. So minerals have to be solid. Our next one is inorganic. That one trips people up for some reason. Organic, inorganic. So does inorganic mean living or does it mean non-living? Yeah, it's non-living. So minerals are not alive. That one's key. They have never been alive and they will never be alive. They're not dead either because they were never alive to begin with. So minerals, some minerals can be made by living creatures. So there are a number of little critters that live in the ocean that make their own shells, and their shells are made out of a mineral that's called aragonite. That's okay. So a creature can make a mineral, but the mineral itself is not alive. It doesn't have the properties of living organisms, like the ability to reproduce, DNA, things like that. So minerals don't have those things. They are non-living. They are not alive. All right, so what do I mean by a definite chemical composition? Minerals are made out of elements. Hey, look at that. We have a periodic table over here. Recognize these guys over here? These are the simplest little bits of matter that make up our world and our universe. And those are what we call elements. And so each mineral is made up of one or more combinations of elements in set proportions. So the mineral quartz is very common. We find it all over the surface of the earth. Its formula is SiO2. So every time we find quartz, it has 2 oxygens and 1 silica. That formula makes quartz, plus some other things. But that formula is very